Hello, and welcome to the Nocturnal Astronomer. I'm your host, Atlas Reed, and tonight we're embarking on a gentle journey through the cosmos to explore one of the universe's most profound mysteries, dark matter. This invisible scaffolding holds galaxies together, shapes the structure of everything we see, and yet remains completely hidden from our eyes. Over the next 2 hours, we'll follow the gravitational fingerprints of this unseen presence, discovering how scientists detect what cannot be observed directly, and why this mysterious substance might make up most of the matter in our universe. If you enjoy these types of videos, I'd love it if you'd give this one a thumbs up and consider subscribing to the channel. And I'm always curious, where in the world are you watching from tonight? And what time is it where you are? Drop a comment below. Alright, let's dive in. Imagine for a moment that you're walking through a forest at twilight. You can see the trees, the paths, the undergrowth. But what you cannot see is the network of roots beneath your feet, a vast underground system that connects everything, providing structure and stability to the entire forest. Dark matter is something like those hidden roots. It doesn't emit light, doesn't absorb light, and doesn't reflect light. Yet its presence shapes everything we observe in the night sky. The story of dark matter begins not with what we can see, but with what doesn't quite add up. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying the Coma Cluster, a collection of over 1,000 galaxies bound together by gravity. He measured how fast these galaxies were moving and applied the basic laws of physics to calculate how much mass the cluster should contain to hold itself together at those speeds. What he found was startling. The galaxies were moving far too quickly. According to his calculations, they should have flown apart long ago unless there was much more mass present than he could account for by adding up all the visible stars and gas. Zwicky called this missing mass dark matter. At the time, his ideas were largely dismissed. After all, suggesting that most of the universe was made of something completely invisible seemed rather far-fetched. But Zwicky had stumbled upon one of the first gravitational fingerprints of dark matter, a clue that would eventually reshape our understanding of the cosmos. For decades, this puzzle remained on the fringes of astronomy. Then, in the 1970s, an American astronomer named Vera Rubin made observations that would bring dark matter firmly into the mainstream of scientific thought. Rubin studied the rotation of spiral galaxies, focusing particularly on the Andromeda Galaxy, our nearest large galactic neighbor. Her work would prove revolutionary. To understand what Rubin discovered, think about how planets orbit the Sun in our solar system. Mercury, being closest to the Sun, orbits very quickly, completing its circuit in just 88 Earth days. Neptune, far out on the edge of the solar system, takes 164 Earth years to complete a single orbit. This pattern makes perfect sense. The farther you are from the source of gravity, the slower you move in your orbit. The same principle should apply to stars orbiting within a galaxy. Rubin expected to find that stars near the center of galaxies would orbit quickly, while stars far from the center would orbit more slowly, just like planets around the Sun. But that's not what she observed. Instead, she found that stars on the outer edges of galaxies were moving just as fast as stars closer to the center, sometimes even faster. This was deeply puzzling. These outer stars should have been flung out into intergalactic space by their own speed unless something was holding them in place with additional gravity. The only explanation that fit the data was the presence of enormous amounts of unseen mass, spread throughout and around each galaxy like an invisible halo. This dark matter, whatever it was, had to be providing the extra gravitational pull needed to keep those speedy outer stars in their orbits. The evidence Vera Rubin gathered came from careful measurements of light. Although we cannot see dark matter itself, we can observe its effects through the motion of things we can see. Rubin used a technique called spectroscopy, which splits light into its component colors, much like a prism creates a rainbow. When a star or gas cloud is moving toward us, its light shifts slightly toward the blue end of the spectrum. When it's moving away, the light shifts toward the red. This phenomenon, called the Doppler shift, is the same effect that makes an ambulance siren sound higher pitched as it approaches and lower pitched as it moves away. By measuring these shifts in light from different parts of a galaxy, Rubin could determine exactly how fast stars were moving at various distances from the galactic center. She examined spiral galaxy after spiral galaxy, expecting to find the pattern predicted by the visible matter alone. Instead, she found the same unexpected result every time. The rotation curves, as astronomers call them, stayed flat even at great distances from the center. Think of it this way. Imagine you're at a carousel, a merry-go-round at a playground. If you stand near the center and your friend stands near the outer edge, your friend has to move much faster to keep pace with you as the carousel spins. That's because your friend is traveling a larger circle in the same amount of time. Now imagine a magical carousel where everyone, no matter where they stood, moved at exactly the same speed. That would only be possible if there was some invisible force acting differently at different distances. The flat rotation curves of galaxies suggest something similar, an invisible mass distributed in just the right way to keep outer stars moving unexpectedly fast. The implications were profound. Calculations showed that dark matter must outweigh all the visible matter in a typical galaxy by a factor of about 5 to 1. In other words, for every kilogram of stars, planets, gas, and dust we can see, there are roughly 5 kilograms of dark matter we cannot detect except through gravity. Other astronomers soon confirmed Rubin's observations in galaxy after galaxy. The evidence became overwhelming. Dark matter wasn't just present in a few unusual galaxies. It appeared to be a fundamental component of every galaxy ever studied, including our own Milky Way. We live, it seems, inside a vast cloud of invisible matter, its gravitational embrace holding our galaxy together. But galaxies aren't the only place where dark matter leaves its fingerprints. On much larger scales, the structure of the universe itself bears the mark of this mysterious substance. When astronomers map the positions of millions of galaxies across vast stretches of space, they find that galaxies aren't distributed randomly. Instead, they're organized into an intricate cosmic web, long filaments and sheets of galaxies separated by enormous voids where few galaxies exist. This cosmic web looks remarkably like soap bubbles or foam, with galaxies concentrated along the thin walls and edges where bubbles meet, and vast empty spaces in between. Computer simulations show that this structure forms naturally in a universe dominated by dark matter. The dark matter acts as gravitational seeds, attracting normal matter and drawing it into dense concentrations where galaxies can form. Without dark matter, the universe would look completely different, likely too smooth and uniform for galaxies to have formed at all. The cosmic microwave background radiation, a faint glow left over from the Big Bang, provides another crucial clue. This ancient light, emitted when the universe was only 380,000 years old, carries within it a pattern of tiny temperature fluctuations. These ripples reflect the density of matter at that early time. The pattern we observe matches theoretical predictions beautifully, but only if dark matter makes up about 85% of all matter in the universe. Normal matter, the atoms that make up stars, planets, and us, accounts for only about 15%. One of the most visually stunning pieces of evidence for dark matter comes from a phenomenon predicted by Albert Einstein, gravitational lensing. Einstein's general theory of relativity tells us that mass warps the fabric of spacetime, and that light follows the curves in this warped fabric. A massive body like a galaxy or cluster of galaxies can bend the path of light passing nearby, acting like a lens. Picture spacetime as a stretched rubber sheet. If you place a heavy ball on the sheet, it creates a depression. Now roll a marble past the ball. Instead of traveling in a straight line, the marble curves as it passes through the depression. Light does something similar when it passes by a massive galaxy cluster. The light from distant galaxies behind the cluster gets bent and distorted, creating spectacular arcs and rings of light around the foreground cluster. By carefully analyzing these distorted images, astronomers can map exactly how much mass is present in the lensing cluster and where it's located. Time and again, these maps reveal far more mass than can be accounted for by visible galaxies, gas, and dust. The extra mass needed to create the observed lensing effects matches perfectly with the amount of dark matter predicted by other methods. One of the most famous examples is the Bullet Cluster, actually two galaxy clusters that have collided and passed through each other. When the clusters collided, the normal matter, mostly hot gas between the galaxies, interacted and slowed down through friction, ending up near the center of the collision. But the dark matter, which doesn't interact with normal matter except through gravity, passed right through, continuing along with the galaxies themselves. Gravitational lensing reveals the positions of both types of matter. The visible hot gas is clearly detected in one location through its X-ray emission. But the gravitational lensing maps show that most of the mass is actually somewhere else entirely, located where the dark matter would be if it passed through the collision without slowing. This provides perhaps the clearest evidence that dark matter is real and distinct from normal matter. The Bullet Cluster is like a cosmic crime scene, with the culprit's fingerprints clearly visible even though the culprit itself remains invisible. Another powerful application of gravitational lensing involves weak lensing, which measures very slight distortions in the shapes of distant galaxies. While strong lensing creates dramatic arcs and rings, weak lensing produces only subtle elongations and stretches in galaxy images. By analyzing millions of galaxies across large areas of sky, astronomers can map the distribution of dark matter in 3 dimensions, creating vast maps of the invisible scaffolding underlying the visible universe. These maps reveal that dark matter exists in halos surrounding individual galaxies, and larger structures surrounding groups and clusters of galaxies, and in the filaments connecting clusters across cosmic distances. The maps match predictions from computer simulations with remarkable precision, providing powerful confirmation that our understanding of dark matter's role in shaping cosmic structure is fundamentally correct. Before exploring what dark matter might actually be, it's worth considering what it definitely is not. When astronomers first realized that galaxies contained much more mass than could be seen in stars, the natural first guess was that the missing mass might be normal matter that simply wasn't bright enough to detect easily. Perhaps the galaxies were full of dim objects like brown dwarfs, which are failed stars too small to sustain nuclear fusion, or black holes, neutron stars, and white dwarfs, the dark remnants of dead stars, or even large planets drifting freely through interstellar space. Astronomers call these hypothetical dark but normal objects MACHOs, which stands for Massive Astrophysical Compact Halo Objects. In the 1990s, several research groups conducted ingenious experiments to search for MACHOs. Their method took advantage of another prediction from Einstein's relativity. If a MACHO passes directly between Earth and a distant star, it should briefly act as a gravitational lens, causing the star to appear brighter for a few days or weeks as the MACHO's gravity focuses the starlight toward us. Researchers monitored millions of stars in the Large Magellanic Cloud, a small satellite galaxy orbiting the Milky Way, looking for these telltale brightening events. They did detect some, proving that machos exist in small numbers. But the frequency of events was far too low to account for the amount of dark matter needed. At most, machos could explain perhaps 20% of the dark matter in the Milky Way's halo. The rest had to be something else. There's an even more fundamental reason why dark matter cannot be made of normal atoms. In the first few minutes after the Big Bang, the universe was hot enough for nuclear fusion to occur everywhere at once. During this brief period, protons and neutrons combined to form the nuclei of the lightest chemical constituents, hydrogen, helium, and trace amounts of lithium and beryllium. The amount of each constituent produced depends on the total density of protons and neutrons in the early universe. By measuring the current abundances of these light constituents and working backward, physicists can calculate exactly how much normal matter existed in the early universe. This calculation, confirmed by observations of ancient stars and gas clouds, tells us that normal matter makes up only about 5% of the total energy and mass in the universe. Dark matter, which accounts for about 27%, must therefore be something fundamentally different from the protons, neutrons, and electrons that make up everything we're familiar with. If dark matter isn't made of atoms, what could it be? One possibility involves particles we already know exist, neutrinos. These ghostly particles are produced in vast numbers by nuclear reactions in stars, including the Sun. Every second, about 100 billion neutrinos from the Sun pass through each square centimeter of your body. You don't notice because neutrinos interact extremely weakly with normal matter. A neutrino could travel through a light year of solid lead and still have a good chance of passing through without hitting anything. For many years, physicists thought neutrinos might have no mass at all, traveling at the speed of light like photons. But experiments in the late 1990s proved that neutrinos do have a small mass. This discovery won the Nobel Prize in Physics in 2015. With mass comes gravity, and the universe contains such an enormous number of neutrinos that even their tiny individual masses add up to something significant. Could neutrinos be dark matter? The answer is no, or at least not most of it, and the reason has to do with speed. Because neutrinos have such tiny masses, even at the relatively cool temperatures of the present-day universe, they're moving at speeds close to the speed of light. Physicists call this hot dark matter because the particles have high kinetic energy relative to their mass. The problem with hot dark matter is that fast-moving particles don't clump together well. Computer simulations show that in a universe dominated by hot dark matter like neutrinos, structure would form from the top down. The largest structures would form first, then fragment into smaller ones. But observations show the opposite. Small structures formed first, then assembled into larger ones through mergers and gravity. This bottom-up pattern of structure formation requires cold dark matter, made of particles moving much more slowly than light. Neutrinos can make up only a small fraction of dark matter, perhaps a few percent at most. The bulk of it must be something else, something cold and slow-moving relative to its mass. This unknown substance became known as cold dark matter, or CDM. When combined with dark energy, the mysterious force causing the universe's expansion to accelerate, this picture is called lambda CDM, and it has become the standard model of cosmology. It explains a vast range of observations with impressive precision. If dark matter isn't made of atoms and isn't neutrinos, what particles could it be? Physicists have no shortage of ideas. The leading candidate for many years has been a class of hypothetical particles called WIMPs, which stands for Weakly Interacting Massive Particles. The name captures their essential properties. They have mass, so they respond to gravity, but they interact very weakly with normal matter through forces other than gravity. The appeal of WIMPs goes beyond explaining astronomical observations. They also emerge naturally from extensions to the Standard Model of particle physics, which describes all known fundamental particles and forces. The Standard Model has been tremendously successful, but physicists know it's incomplete. For one thing, it doesn't include gravity. For another, it contains various parameters that seem oddly fine-tuned, suggesting a deeper underlying theory. One popular extension of the Standard Model is called supersymmetry. This elegant theory proposes that every known particle has a heavier supersymmetric partner particle. The electron has a partner called the selectron, quarks have squarks, photons have photinos, and so on. Most of these supersymmetric particles would be unstable and would have decayed long ago. But the lightest supersymmetric particle, often called the LSP, would be stable and unable to decay into anything lighter. If supersymmetry is correct and the LSP has the right properties, it could be dark matter. In the extreme heat of the Big Bang, supersymmetric particles would have been created in vast numbers. As the universe cooled, most would have annihilated with their antiparticles or decayed. But the LSPs, being stable and interacting only weakly with other particles, would have survived to the present day in just about the right abundance to account for dark matter. The beauty of the WIMP hypothesis is that it makes testable predictions. WIMPs passing through Earth might occasionally interact with atomic nuclei in a detector, depositing a tiny amount of energy. Building detectors sensitive enough to catch these rare interactions has been one of the great experimental challenges of the past few decades. Deep underground, shielded from cosmic rays by kilometers of rock, scientists have built some of the most sensitive detectors ever created. These experiments aim to catch dark matter particles in the act of colliding with normal matter. The underground location is crucial because cosmic rays, high-energy particles constantly bombarding Earth from space, would create far too much background noise. Deep underground, only neutrinos and, potentially, dark matter particles can penetrate. One approach uses tanks filled with liquid xenon kept at extraordinarily cold temperatures. When a particle collides with a xenon nucleus, it recoils, producing both light and electrons that can be detected with extreme precision. The detectors are so sensitive they can measure recoils depositing less energy than the impact of a single grain of pollen settling on a table would produce if scaled to nuclear sizes. These experiments have been running for years, growing ever larger and more sensitive. The Xenon collaboration in Italy, the Lux Zeppelin experiment in South Dakota, and the Panda X experiment in China have all searched for the telltale signals of WIMP interactions. They've succeeded brilliantly at one thing, eliminating background noise and achieving unprecedented sensitivity. But so far, they haven't detected any convincing dark matter signals. Other experiments use different technologies. Some employ silicon or germanium crystals cooled to within a whisper of absolute zero, where even the thermal vibrations of atoms nearly cease. These detectors can measure the tiny heat deposited when a dark matter particle strikes a nucleus. Others use bubble chambers filled with superheated liquids that will form bubbles when a particle interaction occurs. Still others search for the direction from which dark matter particles arrive, hoping to detect a seasonal variation as Earth orbits the Sun and our velocity through the dark matter halo changes. The lack of detection so far doesn't mean dark matter doesn't exist. It means that if WIMPs are dark matter, they interact even more weakly than the original theories predicted, or they're heavier or lighter than the mass range where experiments have been most sensitive. The experiments continue, pushing into new parameter space, but the null results have led some physicists to consider alternative dark matter candidates. One increasingly popular alternative to WIMPs is the axion. These hypothetical particles were originally proposed not to explain dark matter, but to solve a completely different puzzle in the theory of the strong nuclear force. It turns out that the same properties that would solve that puzzle also make axions excellent dark matter candidates. Axions, if they exist, would be extraordinarily light compared to WIMPs, with masses billions of times smaller than an electron. But what they lack in individual mass, they make up for in numbers. The early universe would have produced axions in such vast quantities that their combined mass could account for all dark matter. Unlike WIMPs, these particles would behave more like a wave or field spread throughout space than like individual particles. Detecting axions requires completely different techniques than searching for WIMPs. One method uses strong magnetic fields and resonant cavities. According to theory, when axions pass through a magnetic field, a tiny fraction should convert into photons with a specific frequency related to the axion's mass. By tuning a cavity to resonate at this frequency, experimentalists hope to amplify this faint signal enough to detect. The Axion Dark Matter Experiment, or ADMX, has been searching for these signals for years, gradually scanning through possible axion masses. Like the WIMP searches, it hasn't found anything yet, but it has ruled out certain mass ranges and continues to improve in sensitivity. Other experiments use different approaches, such as looking for axion-induced oscillations in the fundamental constants of nature or searching for axion to photon conversion in the magnetic fields of stars or galaxies. Beyond WIMPs and axions, theorists have proposed a veritable zoo of other dark matter candidates. Sterile neutrinos are heavy cousins of ordinary neutrinos that would interact even more weakly with normal matter. Primordial black holes, formed not from collapsing stars but from density fluctuations in the very early universe, could potentially account for some or all dark matter, though this idea faces several challenges from observations. Some theories propose that dark matter consists of composite particles bound together by their own dark force, analogous to how quarks are bound together by the strong force to form protons and neutrons. To understand dark matter's importance, we need to journey back to the universe's infancy. For the first 380,000 years after the Big Bang, the universe was so hot that atoms couldn't form. Electrons and nuclei existed as a plasma, opaque to light. When the universe finally cooled enough for electrons to combine with nuclei and form neutral atoms, light could suddenly travel freely. This moment, called recombination, is what we observe as the cosmic microwave background. But this wasn't the end of the story. For many millions of years after recombination, the universe entered a period astronomers call the Dark Ages. The background radiation had cooled to invisibility, and the first stars hadn't yet formed. The universe was truly dark, filled with neutral hydrogen gas and the invisible presence of dark matter. During these dark ages, dark matter was hard at work. Even though we cannot see it directly, dark matter responds to gravity just like normal matter. More importantly, dark matter had a head start. While normal matter remained smooth and diffuse, unable to collapse because radiation pressure kept pushing it apart, dark matter experienced no such resistance. It began collapsing under its own gravity immediately after the Big Bang, creating growing concentrations of mass. These dark matter concentrations became gravitational wells, deep valleys in the landscape of spacetime. As the universe expanded and cooled, normal matter eventually fell into these wells. The dark matter halos provided the scaffolding where normal matter could accumulate, reach high enough densities, and eventually form the first stars. This process can be compared to how morning dew collects on a spider web. The web itself is nearly invisible, but the dew reveals its structure. Dark matter is the invisible web, and the luminous matter of stars and galaxies is the dew that makes it visible. Without the web, the dew would have nowhere to collect. Without dark matter, the universe might never have formed galaxies at all. Computer simulations let us watch this process unfold. Starting from the nearly uniform conditions of the early universe, with just tiny density fluctuations, the simulations evolve forward in time according to the laws of gravity and physics. Dark matter clumps together, forming increasingly larger structures. Where dark matter is densest, normal matter falls in, and eventually stars ignite. The results are striking. These simulations produce a universe that looks remarkably like the one we observe, a cosmic web of filaments and clusters, with galaxies forming where the dark matter is most concentrated. Change the amount of dark matter, and everything changes. Too little, and galaxies never form. Too much, and they form too efficiently, creating giant galaxies far earlier than we observe. The amount of dark matter needed to match observations is precisely the amount inferred from galaxy rotation curves, gravitational lensing, and the cosmic microwave background, providing powerful confirmation that this picture is correct. Every galaxy, including our Milky Way, sits at the center of an enormous dark matter halo extending far beyond the visible stars. These halos are not uniform spheres, but have structures shaped by the violence of cosmic evolution. Smaller halos merge to form larger ones, creating a hierarchy that stretches from the smallest galaxies to the largest clusters. The Milky Way's dark matter halo extends perhaps 10 times farther than the visible disk of stars, a vast sphere of invisible matter holding everything together. Our Sun, as it orbits the galactic center, is moving through this sea of dark matter at about 220 kilometers per second. Dark matter particles stream past Earth constantly, a ghostly wind we cannot feel except through its gravitational effects. The structure of dark matter halos has been studied extensively through simulations. These numerical experiments reveal that halos are denser at their centers and become more diffuse toward the edges. They're not perfectly spherical but slightly flattened and may contain substructure, smaller clumps of dark matter that have survived within the larger halo. Some of these subhalos might contain enough dark matter to hold a small population of stars, forming the dwarf satellite galaxies that orbit larger galaxies like the Milky Way. One prediction of these simulations has proven particularly interesting. The models suggest there should be many more small dark matter halos than large ones. Each large galaxy should be surrounded by thousands of smaller subhalos. Some of these contain dwarf galaxies we can observe, but many might contain too few stars to see, or perhaps no stars at all, existing as invisible lumps of dark matter. Recent observations have found tentative evidence for these invisible subhalos. By carefully analyzing the motions of stars in thin streams that wrap around the Milky Way, remnants of dwarf galaxies torn apart by tidal forces, astronomers have detected disturbances that could indicate encounters with dark matter clumps. The stars in these streams should move smoothly unless perturbed by something massive, and the observed perturbations match what you'd expect if dark matter subhalos passed through the streams. The relationship between dark matter halos and the galaxies they host is not simple. While dark matter provides the gravitational well where galaxies form, the process of galaxy formation involves complex physics, gas cooling and condensing, stars forming and exploding as supernovae, black holes growing and ejecting energy. All these processes can affect how matter is distributed within the halo. Despite the overwhelming evidence for dark matter, Some scientists have explored a radical alternative. Perhaps there is no dark matter at all. Maybe instead, our understanding of gravity itself is incomplete, and gravity behaves differently on galactic scales than Einstein's theory predicts. After all, we've never directly tested general relativity on the scale of entire galaxies. The most developed alternative theory is called modified Newtonian dynamics, or MOND. Proposed by physicist Mordechai Milgram in the early 1980s, MOND suggests that when gravitational acceleration becomes extremely weak, as it does in the outer regions of galaxies, Newton's laws need modification. Instead of force being proportional to acceleration, MOND proposes a different relationship that kicks in at very low accelerations. The appeal of MOND is that it can explain galaxy rotation curves without invoking dark matter. With the right modification to gravity, stars at the edges of galaxies naturally move faster than Newton's laws would predict. MOND can also explain certain correlations observed between galaxy properties, such as the relationship between a galaxy's total luminosity and the shape of its rotation curve. These correlations emerge naturally in MOND but require some fine-tuning in dark matter models. However, MOND faces serious challenges. While it works well for individual galaxies, it struggles to explain larger scale structures. The bullet cluster, with its clear separation between the bulk of normal matter and the location of gravitational mass, is particularly difficult for MOND to account for. MOND also has trouble explaining the pattern of temperature fluctuations in the cosmic microwave background and the formation of structure in the universe. More fundamentally, MOND is not a complete theory of gravity but rather an ad hoc modification of Newton's laws. Creating a fully relativistic version of MOND that works in all contexts has proven extremely difficult. Various attempts have been made, but none has achieved the elegance and consistency of general relativity while also explaining all the observations that dark matter explains. Most physicists view the evidence as overwhelmingly favoring dark matter over modified gravity. The fact that multiple independent lines of evidence, from galaxy rotation to gravitational lensing to the cosmic microwave background, all point to the same amount and distribution of dark matter is compelling. Getting all these different observations to agree requires remarkable fine-tuning in modified gravity theories, while in dark matter models they arise naturally from a single underlying cause. The standard cold dark matter model has been tremendously successful, but it's not perfect. Some observations don't quite match predictions. For instance, simulations predict that dark matter halos should be densest at their centers, forming sharp peaks called cusps. But observations of some galaxies suggest their dark matter is more smoothly distributed, with flatter cores rather than cusps. The simulations also predict more small satellite galaxies around large galaxies than we seem to observe. These discrepancies might result from normal astrophysical processes we don't fully understand, or they might hint that dark matter has properties beyond what the simplest models assume. One possibility is that dark matter particles can interact with each other, not through the electromagnetic or strong forces, but through their own dark force. In standard cold dark matter models, dark matter particles are assumed to interact only through gravity. They pass through each other like ghosts. But what if they can occasionally collide or scatter off each other through some new force? This self-interacting dark matter, or SIDEM, would behave differently in the dense centers of dark matter halos. When dark matter particles collide, they exchange energy and momentum. This process, repeated countless times, would tend to even out the distribution of dark matter, smoothing out the densest regions and creating cores instead of cusps. Computer simulations of self-interacting dark matter show that with the right amount of self-interaction, You can reproduce both the large-scale structure that standard dark matter explains and the small-scale properties that match observations of galaxy cores better. The challenge is that the amount of self-interaction has to be just right. Too little, and you get the same cuspy halos as standard dark matter. Too much, and dark matter would clump too efficiently in some environments or be too spread out in others. Finding models that work across all the scales from dwarf galaxies to galaxy clusters requires careful tuning. Interestingly, self-interacting dark matter might also explain another puzzle. Some galaxy clusters contain member galaxies whose cores appear unusually large and diffuse. If dark matter can scatter, a galaxy plunging through a cluster would experience a kind of dark matter friction, with its dark matter particles scattering off the dark matter particles in the cluster. This could strip away the galaxy's outer dark matter halo while leaving its stars largely unaffected, potentially explaining the observations. If dark matter makes up most of the matter in the galaxy, is there dark matter here in our solar system, perhaps even passing through your body right now? The answer is almost certainly yes, though in such tiny amounts that it makes no practical difference. The density of dark matter in our neighborhood of the galaxy is quite low. Calculations suggest about 0.3 protons worth of dark matter mass per cubic centimeter. That might not sound like much, and it isn't. For comparison, the best laboratory vacuums on Earth have thousands of times higher density than that. Even in the vast emptiness of interplanetary space, the density of normal matter from the solar wind is comparable to the dark matter density. Because dark matter interacts so weakly, it doesn't accumulate around the sun the way normal matter does. It simply streams through the solar system in all directions, its density barely affected by the sun's gravity. This means there's no dark matter planet orbiting the sun, no dark matter asteroid belt, nothing of the sort. Just an extremely diffuse background of dark matter particles moving on their independent trajectories through the galaxy. Could there be any effects on the solar system at all? Some scientists have speculated about exotic possibilities. For instance, if the dark matter halo has substructure, with clumps and streams, the solar system might occasionally pass through a denser region. Could this affect planetary orbits? The answer is almost certainly no. The effects would be far too small to measure. But it's an interesting thought experiment. One slightly less exotic possibility involves the Oort cloud, the vast reservoir of comets surrounding the solar system at its outermost reaches, extending perhaps halfway to the nearest star. Some astronomers have suggested that the gravitational effects of dark matter might occasionally perturb comet orbits, sending comets falling toward the inner solar system. However, the effects of passing stars and the tidal force from the galaxy as a whole are much larger than any dark matter contribution. Perhaps the most significant way dark matter affects us is simply by existing. Without dark matter, the Milky Way galaxy wouldn't exist, the Sun wouldn't exist, Earth wouldn't exist, and we wouldn't be here contemplating these questions. Dark matter shaped the structure that allowed our galaxy to form, and in that sense, we owe our existence to it. The search for dark matter continues on multiple fronts. Direct detection experiments keep growing larger and more sensitive, exploring new regions of parameter space. The next generation of detectors, already being designed, will be sensitive enough to detect neutrinos from the sun, which represents both a challenge, as these neutrinos become an unavoidable background, and an opportunity, as it will test the detector's sensitivity to extremely rare events. Particle accelerators offer another avenue for discovery. The Large Hadron Collider at CERN has been searching for dark matter by attempting to create it in high-energy collisions between protons. The idea is that if dark matter particles exist and have masses within reach of the LHC's energy, they should be produced when protons collide at nearly the speed of light. The dark matter particles themselves would escape the detector invisibly, but their presence could be inferred from an imbalance in the momentum of other particles produced in the collision. So far, the LHC hasn't found evidence for dark matter production, but the search continues. Future colliders with even higher energies might succeed where the LHC has not. At the same time, constraints from these searches are helping to rule out certain dark matter models and guiding theorists toward others. Astronomical observations continue to provide crucial insights. New surveys are mapping the distribution of dark matter across cosmic time with unprecedented precision. The Vera Rubin Observatory, which began regular operations recently, will photograph the entire visible sky every few nights, tracking billions of galaxies and using their shapes to map dark matter through weak gravitational lensing on the largest scales. Space-based telescopes looking for gamma rays might detect signals from dark matter annihilation. If dark matter particles can annihilate when they meet their antiparticles, as some theories predict, the centers of galaxies or small satellite galaxies should glow faintly in gamma rays. Several potential signals have been reported over the years, but none has been definitively confirmed as dark matter. The Fermi Gamma Ray Space Telescope continues to search the sky for these telltale signatures. Radio telescopes are joining the hunt as well, searching for the faint signals that axion dark matter might produce in magnetic fields around neutron stars or in intergalactic space. Each method probes different possibilities, different mass ranges, different interaction strengths. Together, they're gradually narrowing down where dark matter might be hiding. As we reach the end of our journey through the invisible universe, it's worth reflecting on how far we've come and how far we still have to go. Dark matter remains one of the deepest mysteries in science, a reminder of how much we have yet to learn about the universe we inhabit. We've followed the gravitational fingerprints of dark matter from the rotation of individual galaxies to the structure of the cosmos on the largest scales. We've seen how it shaped the early universe, providing the scaffolding on which galaxies could form. We've explored the many ways scientists are searching for this elusive substance, from detectors deep underground to observations of distant galaxy clusters. The evidence for dark matter is overwhelming. Multiple independent lines of reasoning, using completely different physical principles, all point to the existence of this invisible mass. Galaxy rotation curves, gravitational lensing, the cosmic microwave background, the formation of structure in the universe, all these phenomena require dark matter to make sense. The alternatives, like modified gravity, struggle to explain the full range of observations with the same elegance and consistency. Yet for all we know about dark matter's effects, its nature remains mysterious. Is it WIMPs? Axions? Something stranger we haven't thought of yet? We know it must be cold, moving slowly compared to the speed of light. We know it must be stable, unchanged since the Big Bang. We know it must interact very weakly with normal matter. Beyond these constraints, the possibilities remain wide open. Some scientists find this frustrating. Decades of searching have not yet revealed dark matter's identity. Experiments have grown increasingly sophisticated, yet detection remains elusive. But there's another way to view this situation. We're searching for something that makes up most of the matter in the universe, something that shaped everything we see, and we're doing it despite the fact that this substance barely interacts with the matter we're made of. The challenge is immense, but so is the prize. Every null result teaches us something, narrowing the possibilities, guiding future searches. Every new observation of dark matter's gravitational effects adds to our understanding of how this mysterious substance is distributed and how it behaves. Slowly but surely, we're cornering dark matter, limiting where it can hide. Perhaps in the coming years, a detector will finally catch a dark matter particle interacting with normal matter. Perhaps a telescope will spot an unmistakable signal of dark matter annihilation or decay. Perhaps a particle accelerator will create dark matter in the laboratory. Or perhaps the answer will come from a direction we haven't anticipated, a new theoretical insight or an unexpected observation that suddenly makes everything clear. Whatever the answer turns out to be, discovering the nature of dark matter will transform our understanding of the universe. It will tell us about new particles and possibly new forces. It will reveal connections between the quantum world of particle physics and the cosmic scales of galaxies and cosmology. It might even point the way toward a more complete theory of nature, unifying gravity with the other forces in ways we can currently only imagine. The invisible scaffolding that holds galaxies together remains invisible for now, but its gravitational whisper echoes through every corner of the cosmos. In following these whispers, we're tracing the outline of something profound, something that makes up most of the universe's substance yet remains tantalizingly just beyond our grasp. The search continues, driven by curiosity, ingenuity, and the deep human desire to understand the universe we find ourselves in. And on that note, we come to the end of our nocturnal journey through the cosmos. I hope this exploration of dark matter has given you a sense of both how much we've learned and how much remains to be discovered. The universe keeps its secrets well, but patient observation and clever thinking gradually reveal its mysteries. Thank you for joining me tonight on this voyage through the invisible universe. Whether you listen to help you drift off to sleep or simply to satisfy your curiosity about the cosmos, I'm grateful you spent this time exploring these ideas together. Until next time, keep looking up, keep wondering, and remember that the universe is far stranger and more wonderful than everyday experience suggests.